Barry from Barry Science Lab, and today we're going to talk about probability. Welcome to Probability Lecture 2. So, last time we talked about combinatorics. It's all about counting. So, we talked about how to count very simple things. There's one over there.
Can we start from left all the way left?
Counting. And we specifically want to view everything as a sequence of events. So, we start with event 1, which has n possible outcomes. So outcome 1, outcome 2, outcome n1. And then each of these outcomes will lead to event 2, and event 2 might have O1, O2, all the way through ON2 outcomes as well, each of which lead to event 3, and some of these outcomes might even lead to separate events, each with their own number of possibilities. And then counting them becomes really complicated because you essentially have to split things into two cases. But in general, the rule is if you have independent events like this, the number of possible outcomes is just n1, n2, all the way to, well, however many events there are. Okay, so that's combinatorics, which is useful in basic probability. But this series is not about basic probability. Probability or combinatorics means nothing if we don't have a formal notion of what probability, what chance means before putting pen to paper. So, what does probability actually mean? That is a very good question, and one that is half math and actually half philosophy. Now, there were two schools of philosophical thought on what probability means. The frequentist side and the Bayesian side. So, a Bayesian, if I were to take the Bayesian model, let's say I somehow calculated that the chance that I have a heart attack right now, or while I'm giving this lecture, is p equals 0.0001. Then the Bayesian model takes probabilities as amounts of belief. So if the probability is 0.0001 that I have a heart attack while giving this lecture, then I generally believe that I will not have a heart attack and make it to the end of this lecture without any health issues. So I don't believe this. Then, let's say I calculate that there's a 0.70 probability that I'm going to pass a certain course. Now, what does that mean? Well, 0.70 is kind of middle of the pack. It means that with the right conditions, the right amount of effort from my end, and the right luck, it could happen. And then finally, let's say I calculate that the probability is 0.995 that I will wear at least one blue shirt in the rest of my lifetime. And, that means that it almost certainly will happen. So I believe that it's going to happen because the chances are so high. And let's say I calculate the probability is 1 that I'm holding a black marker right now. Then I believe that I'm holding a black marker. I believe this will happen. And then the frequentist is on the other end. It's a little bit more mathematical. So it says that probabilities are more like limits. The probability that X will happen, which can actually be denoted as P of X, is equal to the limit as the number of trials you do goes to infinity of the number of trials where you achieved X divided by the total number of trials. So, for example, if I say that the probability is 0.70 of passing a specific course, then that means that if I take this course infinitely many times, then the ratio of the number of times I've passed the course divided by the total number of times I've taken this course is going to approach 0.70. And similarly, if the probability that I'm going to have a heart attack in the middle of the lecture is 0.0001, then that means that if I repeated this lecture infinitely many times, or if I kept giving this lecture over and over and over without regarding age or exhaustion, then the number of times I had a heart attack while giving the lecture divided by the total number of times I gave the lecture would also approach 0.0001. So that's the philosophical end of what probability actually means according to real life. But we can only go so far without formalizing our notion of probability. So it's time to end philosophy class and start talking about what probability means in math, which is kind of detached from this intuitive notion. So, what does probability mean? Well, to answer that, we first have to talk about the notion of a sample space. The sample space of an event is the amount of possibilities that that random event could possibly spit out. So, for example, a die has a sample space. Well, 1, 2, 3. Has a sample space S is equal to 1, 2, 3, 4, 5, 6. Because there were 6 possible outcomes of a dice roll. It lands with one of the 6 numbers on top. So this is what we call a sample space. But sample spaces are not always finite or even countable. They might not just be discrete, but for example, you might have a sample space that ranges over the entire real numbers, or from 0 to 1. So that's what we mean by a sample space. It's going to be any of the possible outcomes that you could get from this random event. And so, you might expect that probability is going to be a function that maps S to some real number from 0 to 1, inclusive. But in actuality, that's not going to be true. Because what if we want to talk about the probability of the die landing on an even face? Or what if we want to talk about the probability of 2 dies giving you snake eyes? We can't do that if we don't allow probabilities take in subsets of the sample space instead of just elements of the sample space. So probability is not actually a function from the sample space to 0, 1. It's a function of something much different. The power set of the sample space. What is the power set? Well, for that, we're going to need to get into measure theory. The power set is a sigma algebra of the set that contains every single subset of the set. Now, in this case, how many subsets are there? Well, this is actually another one of the combinatorial problems that, like the ones that we discussed last time. In this case, we can split it up into 6 events. Why? Because the process of forming a subset is we choose which of the elements within S we want to be part of our subset or not. So event 1 is we choose whether we want 1 to be part of our subset. There are 2 possible outcomes of that, either yes or no. And then event 2 has the same 2 outcomes, and so on and so forth until event 6, which still has 2 outcomes, which means that the total number of outcomes is going to be 2 times 2 times 2 times 2 times 2 times 2, which is going to be 64 possible subsets, which are all in the power set, which is a collection of all possible subsets. So there are going to be 64 subsets within this power set of the sample space. I'm not going to talk about writing them all out because that would take the rest of the time I have for this lecture. But this is actually a mapping from our power set to 0, 1. But are there any other properties we could talk about? Is this it? Well, yes, actually. 3 very intuitive ones that we call the Kolmogorov axioms. The Kolmogorov axioms are 3 specific rules that we define probability by that align with our intuitive notion of it. Number 1, countable additivity. The probability of A union B, where A and B are 2 subsets of the sample space, is equal to, if A and B are disjoint, the probability of A plus the probability of B. And by extension, through some set theory, this leads to the conclusion that in general, without the disjointness, it's the same thing, minus the probability of A union intersect B. 2, the probability of the empty set occurring is 0. Because, one of the events has to occur. There's no way that you can roll the dice and you get no face. Which means that the probability of the entire sample space occurring is 1. Because you're going to get something from the sample space. And finally, number 3. Wait, is there a number 3? Oh. As a consequence of this, that means that the probability of any event, a subset of S occurring, has to be greater than or equal to 0. So probabilities are non-negative. So these are the 3 very intuitive axioms of probability. And now you can see that these define sort of probability in an intuitive sense. So the probability of one of the things occurring is 100%. The probability of nothing occurring is 0%. Well, unless nothing is part of the sample space, which it isn't in the dice roll case. We have countable additivity, and probability always has to be non-negative. This also leads to the caveat that it's between 0 and 1. Okay, but as you'll notice, this has nothing to do with actual randomness. Part of that randomness aspect comes from the Bayesian and frequentist interpretations, but you can also introduce a mathematical object that has those intrinsic random properties. That's what we call a random variable. And this is what we're going to talk about next time. That's it.